Hello my dear friends, in this video we will going to learn the expansion process which is done by Joule-Kelvin. In the Joule-Kelvin expansion, the practical approach, that means practical setup, is like that. There is a pipe like that. There is a pipe, uniform cross-section pipe. This is a uniform cross-section pipe. Take a uniform cross-section pipe, right, in which there is a flow in and the flow is out. Flow out, right? So there is a uniform cross section, right? And from anywhere we install a throttling valve. Install a throttling valve. This is your throttling valve. This is your throttling valve, right? And mind it, the all setup is insulated. That means there is no heat transfer during the flow, right? Now, so what is done in Joule-Kelvin expansion? So there is an expansion. That means if we take two cross section, this is your inlet section 1. Let's suppose this is your exit section 1 dash. Let's suppose we take two section 1 and 1 dash, right? So expansion, that means it's reduced pressure. So it must be P1 dash is less than P1, right? So how can you measure the pressure? You install here a pressure gauge. Install here a pressure gauge which is measure pressure P1, and install also here a pressure gauge which is measure pressure P1 dash. So why this pressure will reduce? Because the friction, because of the friction, because of the friction. So because of the friction, the pressure will reduce. So if you regulate the valve, that means if you gradually close the valve, so first there is open, so there is a flow in and there is a flow out. There is no any pressure difference when there is a fully open. But if we gradually close it, so the passage through which the fluid is flowing is continuously reduced. So if the passage is reduced, the velocity will increase, and when the velocity will increase, the pressure will reduce. So the final pressure at exit section must be reduced as compared to the inlet section. So this is your expansion process. And why this is done? Because of friction. Now, the second thing is that if you measure the temperature here, if you measure the temperature, if you install a thermometer here, if you install a thermometer, right, which is measure temperature T1, and also install a thermometer here which is measure temperature T1 dash. So can you say that T1 dash is less than T1 or T1 dash greater than T1. This may be possible. So how can you say that these two processes are possible? Number first is that due to friction in the pipe, the intramolecular energy will increase. Why? Because there is a friction. So if there is a friction, so their intramolecular energy will increase, and due to increase its intramolecular energy, the temperature at outlet will increase. So it may be. So this temperature is increased. So this temperature will increase is due to friction of the flow, right? But similarly, this temperature also will reduce. So why this temperature will reduce? So, but there may be chance is that when the fluid is expanded, that means that means the pressure P1, the pressure at exit will less than the pressure as inlet. So the pressure will reduce. So due to that, but sometime will expand. So pressure at exit section will reduce. So because of this pressure reduce, there may be chance, may be possibility that it may also reduce its temperature at the outlet, right? So this two counter effect, that means there may be a temperature increase at the exit and there may be temperature reduce at the exit, there may be anything. So these two counter effect condition will depends upon the what is dominant. If there is a friction is dominant, so its temperature will increase. If there is a reduction of the pressure will more, then the temperature will increase, temperature will decrease. So these two counter effect will decide the outlet temperature during the expansion process. So this is known as throttling process, right? This is known as throttling process. So what is done in the throttling process? We apply a steady flow energy equation. Flow energy equation. What is that? H1 plus, sorry, this is your Q1 dot M dot single inlet, so M H1 V1 square by 2 plus Z Z1 is equal to W dot plus M dot H1 dash plus V1 dash K square by 2 plus G Z1 dash, right? So during throttling process, there is no heat transfer, there is no any work transfer, and we neglect change in kinetic energy and change in potential are neglected. We can neglect. So final result is come out to be what? H1 is equal to H1 dash. So that means enthalpy before throttling is same as enthalpy after throttling, right? But one noticeable point is that, but this is very highly irreversible process, but this is highly irreversible process because of friction, because of friction, right? So this is irreversible process. Throttling is the irreversible process. So now if we have done an experiment like that, why? Because the enthalpy, as we know that H is the function of P and T. We take. So if we fix the quantity at inlet, so at inlet P1 and T1 is fixed. If at inlet, if P1 and T1 is fixed, so if P1 and T1 is fixed, so corresponding H1 is fixed, right? So if H1 is fixed by keeping pressure and temperature constant, that means a fluid which is flowing, so at this cross section we measure the pressure and temperature. So at any time, because it is a steady flow, so a steady flow, the property of the fluid doesn't change with respect to time. So at this cross section we take the pressure and temperature will fix. So at this cross section enthalpy will fix. H1 1 is the cross section, not a point. So at cross section 1 the enthalpy is fixed. So if now this is okay. Now if we close the valve gradually, right? First of all, you fix the state point at the inlet section. So what is the fix? If you fix the pressure and temperature at the inlet to the cross section, so corresponding to that pressure and temperature, the enthalpy at a section 1 is fixed now, and that fixed enthalpy you can flow the fluid into the control volume. So if you take this is our control volume, there is nothing is wrong. So this is our control volume. So this is your inlet, it's fixed, H1 and H2. So if you write like that, this is your control volume, and there is a control volume at which the enthalpy H1 is fixed. Now if we gradually close the valve, now we close the valve, so that means if H1 is fixed, now valve is gradually closed. If the valve is gradually closed, that process is known as throttling. Throttling process, that means you throttle the fluid. That means throttle of the fluid. That means what is the throttling of the fluid? That means during the throttling, you fix the enthalpy at a given pressure and temperature. Now we reduce the passage in between that. So if we reduce the passage in between reduce the passage, and through the reduction of the passage, if the fluid is flowing, then that fluid is throttled, right? So if you reduce the passage, so the outlet, so we get different pressure and temperature, like different set, you get different set of pressure and temperature, like what is that, P1 double dash, T1 double dash, P2 double dash, T2 double dash, like that. So different set. So what is that, what is you done, you are flowing the fluid, and if the flowing fluid, you measure the P1 and T1, and corresponding to that, if you put the value of H1, right? And now if you regulate the valve, that means at H1, if you partially close the valve, 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 and according to that, gradually closing the valve, we measure T1 dash, P1 dash, T1 double dash, P1 double dash, T1 triple dash, P1 triple dash, different set of the pressure and temperature. So according to different set of pressure and temperature, corresponding to that, you have H1 double dash, H1 triple dash. So like that, you have this different point at outlet. So this point, and finally, so these points are equal to what value? H1. So this is set number first. Again, the fluid is flowing at a different pressure and temperature at the inlet, a measure H2, and again if you partially close the valve, and corresponding to that pressure and temperature, you again measure this exit pressure at different level. So again H2 set will available, again the fluid is flowing, again the different condition of P1 and T1. According to that, you regulate the valve. Again, the different set of the P2, P3 and T3 will available at corresponding to that. So this, so that means if there is a H1 set, so corresponding to that, you have H1 dash, H1 double dash, H3 double dash, like that, right? Again, you have different set H2 at a different pressure and temperature at inlet. This is at inlet. This is at inlet. So this is at exit. Exit, and this is your inlet. So at inlet have H2 and different set H2 dash, H2 double dash, H3 double dash. You have again H3 at inlet, so H3 dash, H3 double dash, H3 triple dash. You have again different set corresponding different pressure and temperature. So if you plot, so we draw a plot that is like that. If you draw a plot like that, this is your temperature and pressure. Mind it, in the throttling process, the pressure will always reduce. So there is a different set of the enthalpy line. So if there is a, let's suppose this is point number 1, where the locus P1 and T1 corresponding to that H1. Again you have P2 and T2 at exit. Again it is 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 exit. Again you have inlet section at a different point. So at exit have a different locus. Exits have a different locus. Again you have inlet at a different P1 and T1. So again it have different locus. Again you have different locus. So if you join all these curve, why? Because this is irreversible, so you join dotted line. This is corresponding to H1. Again you join this curve. This is corresponding to H2. Again you join this curve. This is corresponding to H3. So you have a constant enthalpy line. So what is that? This is your P1 T1. And what is this? This is your P1 dash T1 dash. What is that? P1 double dash T1 double dash, like that. This is your point. And what is this point? P2 T2 at inlet, and corresponding to that P2 dash T2 dash, corresponding to that P2 double dash T2 double dash. So there is a enthalpy H2. Again inlet condition P3 T3, corresponding to that exit P3 dash T3 dash, P3 double dash T3 double dash, P3 triple dash T3 triple dash, and all the enthalpy corresponding to this are same. So this is isenthalpy. So this is your, this is a different locus. So this is your locus, different locus. So this is your, nothing is that, this is your locus of constant enthalpy line. Locus of constant enthalpy line, right? And these all are constant enthalpy line. Constant enthalpy line, right? So you draw a plot like that. Now if we repeat this experiment, so this is the repeat. If we repeat this experiment, that we now change the inlet condition. So we change the inlet condition. Let's suppose P2 and Q2, some other value corresponding to the other enthalpy H2, corresponding to generate other outlet condition like that P2 dash T2 dash P2 double dash T2 double dash, like that, and these all points have a same enthalpy line H2. Again you change inlet condition. So repeat inlet condition, corresponding to that inlet condition we have an enthalpy, fix the enthalpy, and you regulate the valve. That means you gradually close the valve, and we found the different P and T1 set, and that all the P1 and T1 set like the same enthalpy line. So we do so. So if you do so, this will look like that. So if you do so, this will look like that. If you do so, this will look like that. 1 minute. If you do so, this is your look like that. This is your what? Temperature and pressure, right? So if you draw a curve like that, let's first of all we draw a curve. So you have a different set of a curve. You have a different set of an isenthalpy line. You have a different set of isenthalpy line. Like that. You have a different set of isenthalpy line. Like that. You have a different set of isenthalpy line. Right? Like that. You have a different set. And also in there. Right? So you have a different enthalpy line. So this is your different locus. So this is your locus of pressure and temperature. So this is your locus of a corresponding enthalpy, right? This is your locus, like that. Okay, like that. So this is your, let's suppose H1, H2, H3, H4, H5. This is isenthalpy, right? So what you observe that, number first, take any curve. Let's suppose we take any curve. Take any curve. Let H3. We take H3 line. We take this line. We take this line. H3 line. This is the isenthalpy line, right? We take this line. Curve. We see that any curve. We see that some part of the curve, the slope is positive. That means if this curve, the slope is positive, and this curve, the slope is negative. So the some part of the curve, the slope is positive, and the some part of the curve, the slope is negative. That is, what is the slope? dt over dou t over dou p. This is the slope at which enthalpy H have two value. Some part there is a positive and some part there is a negative. So there is two value, right? So if dou t over dou p at in constant enthalpy is positive and dou t over dou p at constant enthalpy is negative, some part. So from your observation, so in the throttling process, pressure will always reduce. So if we reduce the pressure, so if you have a point this one, and if you reduce the pressure like this point, if you reduce the pressure, see, if you reduce the pressure, if you reduce the pressure, if you reduce the pressure, the slope is positive, then the temperature also reduce, right? So this is the positive slope. This is the positive slope, and this is your negative slope. So in the case of positive slope, if pressure will reduce, the temperature also reduce. In the case of negative slope, if pressure is reduced, temperature will increase. Why? Because there is a negative. So in the negative slope, there is a heating. So there is a heating. And in the positive slope, there is a cooling. So there is a two zone. There is a cooling zone. If you go from point this to point this, and if you go from this point to this point, you go from this point to this point at the same enthalpy, there is a heating, right? So as we go on increase the temperature, the maximum point of the curve shifted if we increase the temperature. So if we increase the temperature, if the temperature is increased, so there must be, if you go on increase the temperature, if the temperature is increased, the maximum point of the curve is shifting the right. If you increase the temperature, the maximum point, this is a maximum point, This is the maximum point, this is the maximum point, and mind it, at the maximum point, what is the slope? Dou T over dou P at any enthalpy is 0. The slope is 0. So at a maximum point, the next point observation is that as increase the temperature, so as go on increase the temperature, as go on increase the temperature, the maximum point of the curve shifting the right. First it will shifting the right. See, if you increase the temperature, it is shifting the right. Then again it shifts towards right. Number first observation, if you increase the temperature. So what is that? This is the practical plot. If you done a job, this is a practical. So when you draw a graph, just say you like a stress strain diagram. If you draw a stress strain diagram, so there is a practical representation. Nothing is logic behind that. But what is the logic? That the interpretation of that graph is very important. So this graph is the practical. This graph is the practical. We plot according to practical approach. And when it's plotted, what is the conclusion? It is very important. So the first conclusion is that when we increase the temperature, the maximum temperature point, first it shifts to right, and then it shifts to left. Right? Number first. And what is the number third? Second. Number second is that, and if you join this maximum point, at which dou T over dou P at a constant enthalpy is 0, that is, join the locus of dou T over dou P at constant enthalpy is equal to 0, then we find the another curve, red dotted curve, known as inversion curve. So what is that? As and if join this maximum point at which dou T over dou P at enthalpy is equal to 0, that is, join the locus of dou T over dou P at constant enthalpy is equal to 0, then we find an other curve known as inversion curve. So what is the inversion curve? Inversion curve is nothing. It is the curve which is drawn by the locus at which dou T over dou P at a constant at a given enthalpy is 0. Right? Now, so this is your inversion curve. So this red dotted line is called inversion curve. Right? Now next, the inversion curve, and next point, this inversion curve cuts on the temperature axis at 2 points. See, very important. So this inversion curve cut the temperature axis at 2 points. That means maximum inversion temperature and minimum inversion temperature. And above the maximum inversion temperature and below the minimum inversion temperature, the constant enthalpy line is only negative slope. See, this is the negative slope. Slope is reduced, slope is reduced, slope is reduced. So if the slope is negative, then always heating, there is no any cooling effect. So what is that? Next point from the graph, what we conclude that the inversion curve cuts the temperature axis at 2 points. That is T max maximum inversion temperature and T minimum inversion temperature. And above T max and below T minimum, the constant enthalpy line is only negative slope. That means always give what? Always give negative slope. So always give heating effect. So if you have point this one, if you have this point initially P1 and T1, and if you throttled it, that means if you reduce the pressure, see its temperature will increase. So it is a heating line. Above this point, if you have this value P1 and T1, if you increase, so if you decrease the pressure, so its temperature will increase. So above and below the inversion point, there is always heating. There will no chance of cooling. Now, so next point is that, again next point is that, what is that? See, very important. If we throttle the fluid the fluid at positive part, that means if this is your point number 1 and this is point number 1 dash, let's suppose throttle the positive slope part. This is your positive slope. This is your positive slope. So if we decrease the pressure, the temperature also decrease. See, if this is your temperature T1 and this is your temperature T1 dash. So if we, in the case of positive slope, if we decrease the pressure, throttle matlab decrease the pressure. If we reduce the pressure, that means expand the pressure, the temperature also reduce. Therefore, the zone of positive slope always a cooling effect. If other point is in positive slope and start throttle always, if our point 1 is in a positive slope and start throttling always gives a cooling effect. But if the fluid throttled at a positive slope, that means if you reduce the pressure, then temperature always increase. Therefore, a zone of a negative part, the slope represents the heating effect. So this is your heating effect. Hence, it is the inversion curve. Which represent the cooling and heating region, which separate. Hence, this is the inversion curve which separate the heating and cooling region. So 3 points must be remembered in the inversion curve. So what is the inversion curve? The inversion curve, it is a locus of It is a locus of a point at which the slope of a temperature versus pressure at a given enthalpy is zero. Number first. Number second, if we increase the temperature, so number first point very clear. How can you develop inversion curve? The inversion curve will develop. It is the locus at which the maximum temperature. That means at that point the slope of that point, it must be zero at a given enthalpy. Number first, and draw a locus. Number second, if we increase the temperature, the inversion curve first is in right side, and after certain value it will shift towards a left side. Number second. Number third, it is the inversion curve which separate the cooling and heating zone. Right? Number third. Number four, above the inversion curve and below the inversion curve, the slope always negative. That means if you throttle above the inversion curve and if you throttle below the inversion curve, the process always gives the heating effect. Why? Because the temperature must be increased. Right? So these are the some facts about the inversion curve. Now, next is that, see, very important. If we find the maximum cooling effect, so next point, if we find the maximum cooling effect due to throttling, then our initial point should be at the inversion curve. Very important. So if our point is this one, initially our point is at 1, and if you throttle, the maximum cooling effect is this one. But if our initial point is this one and throttle this point, there is a maximum cooling. Right? Similarly, if our point is this one and if you have a heating, so this much as a heating, but at the inversion curve, maximum heating. So what is given that if you have a maximum cooling, if you define, that means if you have a maximum cooling, so our starting point, that is inlet point is at inversion curve. Right? So if we find the maximum cooling effect due to throttling, then our initial point should be at inversion curve. That is, for a maximum cooling, our point start. So our point start where? Dou T over dou P at constant enthalpy is 0. यहाँ से हमारा point start होना चाहिए. Right? If you throttle, next, very important, I am telling you. So this is our graph initially. So very important. This is your temperature and this is your pressure. So if this is our inversion curve, right? And let's suppose this is our enthalpy H, right? If we throttle from heating region, so let's suppose our initial point is somewhere here. Let's suppose our initial point is 1 here, right? And if you throttle from a heating region, so this is your heating region. If you throttle from a heating region up to a cooling region, throttle a heating region up to a cooling region. So if our point, let's suppose one point is here, other point is here, or other point is here. Let's suppose different point, 1 dash, 1 double dash, 1 triple dash. Right? So let's suppose our initial point is here, heating region. So our initial point is if you draw rather than a large. This is your very important temperature and pressure, and this is our inversion curve, no problem, right? And this is our, let's suppose this is our isenthalpy line, right? So this H is constant, right? Let's suppose our initial point is somewhere here, 1 H, let's suppose H, right? So if you draw a throttling process, so if you move along this direction, let's suppose if you throttle from a heating region, this is a heating region, in this there is a cooling region, this is a heating region, up to a cooling region, throttle, this is a cooling region, so if you, this is very important, if you have a point in heating region and throttle up to cooling region, so cooling region, it may be here, it may be here, and it may be here. This is a cooling region. So if you take point 1 dash here, 1 double dash here, 1 triple dash here, right? So this is the beauty. Let up to this extent, then so if we throttle from point 1 to 1 dash, though there is a cooling region, but it not be cooling, rather it is heating. See this temperature difference, the temperature will increase. So up to this there is a heating, though there is a cooling, but this is a heating effect. But if you throttle up to this point, so if you draw this line in the cooling region, this is laser. So this is the same temperature. So neither cooling nor heating. But if you throttle up to this level, so this is your cooling. So there must be a cooling. So if you start the point in a heating region, if you take a point in a heating region and you start of the throttle, so it may not sure that it always gives cooling. It may be heating, it neither heating nor cooling, or it may be cooling, right? So if we throttle from a heating region, so what is your conclusion? So if we throttle from a heating region, up to a cooling region, there may not gives always cooling. This may give either heating also, neither heating nor cooling, or cooling. So if you find the cooling effect, so we throttle the maximum throttling possible, but practically it is not done. But if someone you ask, when you are hitting region, when you are starting throttling from a heating region and you go from a cooling region, is there cooling or heating, or what is that? So you can say that either it is heating, either it is cooling, or it is possible that neither heating nor cooling. But other point, this is very important again, But the next point is that, what is that? If we look like that, but if we throttle from, see, but if we throttle from heating region, repeat, but if you throttle, but if you throttle from heating region to a cooling region out of this point, then there will be cooling. Hence, if our initial point is heating region, then we cannot say conclusively that there will be no cooling, right? So if you are heating effect and if you throttle, then you cannot say that there is a heating always. It may be heating, it neither may be nor heating nor cooling, or it may be cooling. So hence, if our initial point is at point heating region, then we cannot say conclusively that there will be no cooling. If the cooling possible, that is depends upon if cooling is possible, that depends upon level of throttling, that is decrease in the pressure is very large. That means decrease in pressure very large, but usually it is not happen. Usually it is not happen, right? Now, okay, if we select the type of a curve which is above the inversion curve, see, if we select a type of a curve above the inversion curve, this is the inversion curve, maximum temperature curve is only negative slope, so there no way to cooling is possible. Similarly, below the minimum inversion temperature of the inversion curve, cooling is not possible because slope is also negative. So from this, hence, from this conclusion we can say that hence cooling not be done above or below the maximum and minimum temperature of the inversion curve. Right? Now, next point, see, so dou T over dou P, the slope between temperature and pressure and enthalpy, is known as mu J, known as Joule-Kelvin effect. This is known as Joule-Kelvin. So if you derive the expression a little bit, so we know that what TdS is equal to dH minus VdP, right? So if you find dH is equal to, what? TdS plus VdP, right? And this is your heat, reversible process. So if TdS, so from this internal energy from the above, we can write that Cp dt minus T dou V over dou T at constant. This is previous lecture, just previous video. You may see that dP, right? So if we write that Cp dt plus V minus T dou V by dou T at constant pressure dP, right? If throttling, that means H is constant So this dH is equal to 0. If this dH is equal to 0, if this dH is equal to 0, so if you rearrange like that, dou dt over dP at constant enthalpy is equal to 1 upon Cp V minus T dou V by dou T at constant pressure, right? At constant pressure, this is equal to this is what? This is your Joule Thomson coefficient Buche. So for an ideal gas, we know that Pv is equal to R into 2. If you differentiate dou V over dou T at constant pressure is equal to R by P is equal to V by T. If you put this value dou V over dou T at a constant pressure is equal to V by T, this will cancel out. So mu J is equal to dou T over dou P at constant enthalpy is equal to 0. So therefore an ideal gas, hence for an ideal gas at constant enthalpy, no change in, so for an ideal, so it is very obvious that an ideal gas at a constant enthalpy, at a constant fund, no change in temperature with respect to pressure. Hence for an ideal gas at constant enthalpy, there is no change in temperature with pressure, right? So that means hence for and hence what is that? That means the temperature, it is not a function of pressure at a constant enthalpy. So at ideal gas, the enthalpy, so for an ideal gas cannot be cooled by a throttling process. So this is 0. So what is that? This is 0. So hence ideal gas, the gas cannot be cooled by a throttling process. That is Joule-Kelvin expansion, the throttling process. So for an ideal gas, the gas cannot be cooled with by throttling process. That is Joule's experiment. Right? Now, so why it is done? Example like hydrogen H2. The maximum inversion temperature is T max 204 Kelvin. So it is all obviously above the room temperature, right? Like that, nitrogen maximum inversion temperature, it is approximately 604 Kelvin. Similarly, air, it is the maximum temperature approximately 794 Kelvin. Similarly, carbon dioxide, it is the maximum temperature 1250 Kelvin. So it will never cool directly. It will never cool. So the first of all, what is the mechanism if the temperature so is higher than the inversion temperature? So if you compress the gas, so what is that? So if this temperature This all temperature is above the atmospheric temperature, 273. That means this temperature is, this all temperature is below the atmospheric temperature, 273, if you done the experiment like that. So 273, that means this is the maximum temperature, inversion temperature, and our temperature initial value is 273, which is above that inversion temperature. So like that, if you have T and P, and this is an inversion, so this is a curve, this is your T max. So this is your T max, but our initial point is like that. Example, T is equal to 273 Kelvin. So this temperature is above that. So if you throttle this, so it is not cooling, it is heating. Basically it is not cooling, it is heating. Why? Because this temperature you have done experiment, but our inversion temperature is this one. So above this, if these all have this all value have a maximum inversion temperature, so it cannot be cooled. So how can it cool? Then first of all, it is pre-cooled it by some other process. So it will pre-cooled by some other process and reach the temperature below the maximum temperature. This cooled and it below the maximum temperature, somewhere here, inversion temperature, then you have start the throttling process. So for an ideal gas, you can never be done the throttling directly. First of all, you do a pre-cooled, that means the temperature below that the maximum inversion temperature, and then start to throttling. Similarly, if there is a inversion temperature, such a high temperature, so if you compress that gas, so the pressure will high, so the gas will increase its temperature. Now it cooled the gas by a coolant at a constant pressure. Then the gas temperature comes down at a certain value, that is below its maximum inversion temperature. Then you throttle the gas, that is temperature of the gas, you get a cooling effect. So what is that? First of all, if there is a temperature, maximum inversion temperature is given, so if you compress the gas, so pressure will increase, temperature will increase, and at, let's suppose, pressure P2. So this pressure, at this pressure P2, you have use a coolant and you cool that. If you cool that, the temperature is reduced. And how much reduced? Below its inversion temperature. If once it below the inversion temperature, start throttling. It is very frequently asked in interview. So what is that? So in this case, you cannot directly cool throttling the process. If the inversion temperature is, the temperature of the gas is as inversion temperature, so you cannot directly done a throttling process. But if you done a throttling process, first of all you compressed it. If you compress it, the pressure will increase, temperature will increase. Right? If you compress the gas, the pressure will increase, consequently the temperature will increase. So at a constant pressure, you cool the gas. If you cool the gas at that pressure, the temperature will reduce. And the temperature will reduce up to what level? Up to below the maximum inversion temperature. When you reaches the below the maximum inversion temperature, then you start the throttling. Then you gives a cooling effect. Okay? This is the process. Okay? Thank you very much.